What is up, guys? How's it going? So today we're going to be continuing how to build a class declaration or how to parse a class, part 2. And today we're going to kind of revisit some of the code that I kind of showed you guys before. So we're going to go back into parsing a reference pointer, and I'm going to explain exactly what a UType is. So I know I skipped over this before, so let's get right into it. So whenever you're parsing a reference pointer, we've already seen all this code, right? We've seen the code that happens before you parse the first identifier. We want to check to see if we have an operator. That way we know whether or not we have an operator symbol. And then we parse our identifier, and then we do a check to see if it's not a dot class, meaning that it's an expression. Then we just keep looping through, so on and so forth. So now we have this code here where it says parse a UType list. So what a UType list is it's basically a list of UTypes. So you're going to want to create an AST called AST UType list, and you're going to want to create a parse UType function. Now you can just create the blank function for now, and I'll get into it in a little bit to explain what a UType is. But after we parse our UType, of course we pass in our branch because we need to add it to the appropriate AST. We then say we want to do a while loop, and while there's a comma, we want to expect a comma, and then we want to expect another UType. We just keep doing that until there's no more comma to the right of the actual UType. So for this example, this would be an example of us saying list of type string, and because we know that the list class only requires one generic type, we just put one UType inside of there. If list required more, then we would put something else like, I don't know, maybe int or something like that. So instead of list, let's say maybe we had like a map of some sort, then we would do that. All right, so now let's go into parsing a UType. So let me explain what UTypes are. UTypes are very powerful when it comes to my language. Like, it encompasses all of the necessary information for running our type system, and it's really cool. So we'll get into a little bit more of the theory behind UType and how it works in the compiler, but for right now, I'm just going to keep things pretty simple. A UType is short for a unique type. Basically, a UType is supposed to represent some type of unique type. So like this class is a type, this string class is a type, this list class is a type that has encapsulated another type through generic typing. I know I keep saying the word type, but you guys get the point. Um, we have like int, so that's also a UType as well. Or we also, UTypes also encompass native types. So like var is a native type. We have underscore int 8 as a type, or int 64, so on and so forth. So those are natives as well. Object is also another one that's a native type. So that's kind of what UTypes represent. So let's just kind of look to see how we do it. So first we create our branch for UType. We then call parse type identifier. Now, before I get into what a type identifier is, well, I mean, the function kind of explains what it is, but let's just kind of go on the outside to see what happens if this is successful. So parse type identifier returns a Boolean, and if it successfully parsed a UType, then we check to see if there's a left brace or a right brace. So like you may have a situation where, I don't know, you have like an object array or a list of type int, and like maybe you have a list of type int array, something like that. So that's why we want to do that. So we want to check to see if peak at 1 is left brace and peak at 2 is right brace, then we want to do that. And the reason why this is very important. You want to check to see if they immediately follow each other, like the left and the right brace, because you don't know, like as a compiler, you don't know what the heck's going on. So there might be a situation where you have something like that, and you just don't want to process that because this is technically an expression. So like if we did something like this, I mean, this doesn't make any sense, but like let's say you had like some variable here called my array, and you wanted to assign the address to my array at 90 at the index. So you just want to make sure that following the UType, you have direct left and right brackets. there's that, and then of course we return true regardless of whether or not we found the left or right braces. Otherwise, we want to complain and say expected native type or reference pointer. And obviously, if we didn't parse our type identifier, it returns false. So once we go into here, we can see our type identifier function. We've mostly already written all the code. So we have our type identifier. We create the AST branch of AST type identifier. We advance one character, and then we check to see if it's a native type. So we get the current token, and is it a var, is it an object, or is it like one of these native supported integers? So is it one of those, or if it's not, then obviously we want to decrement the current token. But if it looks like we have a native type, then we're good to go. All we have to do is just say branch, we want to add the token, so we want to add the native type, whether it's var, object, or whatever. And we immediately want to return true. So if we have like a var here, we can have like a var array, or we can have like an object array. And once we process object, it's going to return out, and it's going to then process these two brackets. So once we have that, our errors is going to be set to protected mode. Now, this is very important. This is where we start getting into complex error reporting. So I don't remember if I've gone over this before, but I'm just going to briefly go over it. I think I have in one of my previous videos, but basically what protected mode represents is when you're compiling things, right? You want to complain about things in the compiler, but you maybe want to hold back on those errors because, I don't know, maybe it just doesn't turn out the way you're expecting, or you're testing for something, right? So you test for this thing, it doesn't work, then you test for this other thing, and then you can just kind of decide what to do from there. So what error protected mode does is it enables protected mode on the error management system, and we just add a possible error list. And what that does is that adds a list, or it adds a list to the stack of potential errors that could be reported to the error management system. All right, so I'm going to go back. And whenever you have your potential, once you put yourself into a protected mode, you have two options. You can either pass, which basically means, I'll pass, I'm not going to report any errors. So what it does is it resets the last checked error to just an empty error, and then it removes the possible error list. So what we want to do is we want to get the last error management, or the last potential errors list, by getting the errors size -1 from the possible errors list. It's just a list that holds a list pointer. So that's kind of why it's like that. Then we want to check to see if our possible errors is empty. And if so, then protected mode is automatically set to false. We pop back, we want to make sure we pop back the last list of errors, but we want to clear and then delete the errors once we kind of do that. So we just want to make sure we free up our memory here. But yeah, that's what happens when we call pass. So otherwise, if we don't want to pass, if we want to explicitly fail, then what's going to happen is we're going to call this, and what the error management system is going to do is it's going to check to see, all right, well, do we have any possible errors? If so, we go through and we get the current possible errors list. We go through all the errors, check to see if we should report it, because maybe depending on whether we reported the error before or not, we don't want to keep doing it, so we just kind of put that in there. And you guys have seen this logic before, so you kind of know what's going on here. We reset the last checked error, we remove the possible errors list, and then we finally do a check to see if possible errors is empty. And if it's empty, then we set the last checked error, or the last error that we reported, to the last checked error. I know this is kind of stupid, but then we set errors to true. So that's what I do for fail. So basically the concept of fail is if you had any errors reported while you were in protected mode, print them out, otherwise nothing happens. All right, so once we enter protected mode, we parse a function pointer. And if we parsed it successfully, we want to fail because we want to print out any errors that may have been related to parsing this. Otherwise, we want to pass because obviously that's broken, or maybe something went wrong in here, that it's not a function pointer. And then we want to free the last sub. So this is very important. when we go to parse a function pointer, and I'm going to get to this in a few minutes, you want to make sure that if you're creating any branches, you want to make sure you free them up. So if we're not going to use this, if we're going to completely ignore the errors that were generated from parsing this function pointer, you also want to make sure you free the last branch that was created as a result of this function call and any subsequent branches below it. So once we do that, you guys have already seen the code for parsing a reference pointer. We just parse a reference pointer and we just do whatever we need to do here, and then we return whether or not we were successful from type identifier. So before I actually show you guys how we parse protected mode, let's kind of look at the grammar for it. So here I'm going to do this. I'm going to go here and I'm going to search for, here I can't even find it. Okay, so here's the syntax for a function pointer. So effectively what function pointers are, and by the way, if you guys were paying attention, I've actually just recently did a refactor. So before function pointers, the formatting was this. You had a function, your pointer, and then you put in your you'd format it like this. So it's kind of like creating a function. So you'd have your type here, and you'd have arg1, and it would be a type of string. And then you'd have your arg2, blah, blah, blah. That is not the format anymore. This is very ugly formatting. Not to mention, because of this formatting, I couldn't have function pointers in my language be returned. I couldn't return a function pointer because of this wacky syntax. It just wouldn't have looked correct to be doing all this garbage. So here is the new syntax of function pointers. It's going to look exactly like this. Pointer, and it looks both this way for return types as well as types being assigned to fields. So you have your variable name here, you have this denoting that I'm going to put a type after it, and then you just have this. So the code that's inside of here represents your parameters. So you can say arg1 type string, say arg2 of type int, right? And then you could do that, or you don't even have to, whoops, and here's supposed to be a comma, or you don't have to actually do that. You can just put the type in, right? So if you don't want to put the actual variable name, then you can put the type. And then in this parentheses, this represents the return type. So I don't know, um, let's say it returns an object or something, right? So this would be your return type. And because this works, because of my language being cyclical, you can literally have a function pointer that returns another function pointer. Then that function pointer can then return more function pointer. I know this is like disgusting, but because of how my compiler is written and everything, this actually works out quite well. And it's actually quite easy to make this work properly. So let's actually go into function pointer. And when you're building your language, I again want to stress the importance of focusing on your grammar, because I know I haven't been using this grammar sheet that much for the purposes of this tutorial, because I've already went through the pain of going through and creating this grammar sheet. But as you're building your language, you're gonna need to use this like 90% of the time while you're building your parser. So if we go here to parsing a function pointer, first you're gonna create a function pointer branch. Once you do that, you create a left paren. After you do that, you want to peek to see if there's a left paren, right? And you want to return false. So if you are parsing a function pointer, right? And let's say we're parsing this type. So we're parsing address. We're going to try to parse a function pointer first. So when we get to object, well, this isn't going to be a left paren, so we're just going to return false. But again, we created this branch underneath the higher level AST, so that's why we have to destroy it. But if it appears to be, the next character appears to be a left paren, then we want to parse what's called a UType arg list optional. And I know it's a bit of a weird way to put it, but what these are considered, UType args. So if you kind of follow along with the wording of my grammar and how I name things in my programming language, you'll start to see as we build on this, they kind of make sense, right? This is considered a UType here, so like object array. This is considered an argument, and this argument is inside of a list, and it's thus the word UType list arg. But in this case, it's a UType list arg optional, which basically means that it's optional for you, like the user's not required to write out the actual name of the argument. It's like if you're creating a function called foo, you can't do that, right? Because you need to know what the name of the variable is to be able to use it. So you'd have to say name. You'd actually have to provide the name of the function. So this would actually be a UType arg list instead of UType arg list optional. But anyway, yeah, so if we go into parse UType arg list optional, we're going to create another branch called this crazy thing here. We're going to immediately expect a left paren. So there are certain functions in my parser where I just know what it's going to be, right? So if I'm peeking that we have a left paren, UType arg list optional assumes its own formatting. So if I go to my grammar here and I find UType arg list optional, you can actually see here that it has the formatting as follows: our left paren, UType arg optional, comma, another UType arg optional, and the star represents it could be 0 or more of this, right? So you can have an infinite amount of arguments, and then you finish it off by having the right paren. And when you look at UType arg optional, so what this shows is that our identifier is not required, it's optional, and then this is what's required. So if we go here, UType arg list optional, we expect the left paren, we peek forward to see if it's a right paren, if so, or we peek to see if it's not a right paren. Because if it is a right paren immediately following this, well, that's totally fine. You can have 0 arguments, so we just parse or we expect the right paren. But if it looks like the character after this is not a right paren, then we parse a UType arg optional. And we do what you saw in my grammar sheet here, which is a indefinite amount of commas in UType arg lists. So it's not required, so we just peek to see after we parse the first one, do we have a comma, expect it, parse the same thing, go back up to the top, and just keep doing it all over again. So if we go into UType arg optional, then we create a branch called UType arg, and we check to see if it's a variable declaration. So we check to see if it's an identifier, basically, which means that it's a potential variable declaration. And then we check to see if the next character is this thing. So if it's this, then we expect an identifier, we expect this character, and then we get the type. We parse a UType. Otherwise, we just parse the UType, and if that's true, return true. Otherwise, we say expected native type or reference pointer. Now, this isn't necessarily required. Like, I don't even have to do that because I'm doing it here in UType. So I'm just gonna do this instead. Take this and return parse UType, and it will actually handle creating or running the error for me. So that way I don't have to actually do it. So if we go back, so now we've successfully parsed a UType arg optional. We've successfully parsed a UType arg list. Let's go back. After that, we want to parse, or we want to check to see if the next character is equal to a left paren. So if it is, then great. We want to expect the left paren, and then we want to check to see if the next character is not a right paren. If it is, then we just skip over all this code and we expect the right paren as follows, and then we return true. Otherwise, if it's not, then we want to create another branch inside of this branch. So we pass, instead of passing AST, we pass branch for getting the next branch of, yeah, I don't want to keep saying the word, but you get the point. It's just creating a branch off of this AST. And then we create a AST method return type, and then we check to see if the next character is equal to nil, which is basically void in my programming language. So by default, functions don't have to return, like they don't have to specify that they don't want to return anything. If you don't want to return anything, just don't put anything there. But if you do, then I don't know, let's say you want to return a number, then you can specify I want to return an int. Well, nil is just my own version of saying void. So that's what that means. So we expect nil. Otherwise, we parse the UType, and then we expect the left paren. So this is important. If we start processing a function pointer and we process a left paren and we parse a UType arg list, it will only return true if there's another left paren. So like what that means is if you have something like this, well, this is not a complete function pointer. If you want a full function pointer, then you're going to have to return, or you're going to have this as the second portion of it to denote that you're returning something. So now we've finally also successfully parsed a function pointer. Now, if we go back to parse type identifier, I've successfully shown you how to parse a function pointer. I've successfully shown you how to parse a reference pointer. And because of that, that means that I also have shown you how to parse a UType successfully. So now we're back at processing or parsing a class declaration. I think the last thing that I didn't show you was parsing a reference pointer list. All it is you just parse a reference pointer once, you check to see if there's a comma, you expect the comma, and then you parse it again. You just keep doing that. So that's pretty much it for today, guys. Hope that made sense. If you guys have any questions, as always, put them in the comment section below. And this, to be honest, for me is like the most boring part of writing a compiler. I absolutely hate it, writing the parser. It just is the way it is. Once we get to the actual backend side of the compiler, it's going to be a lot of fun. So I'm definitely excited for that. But just before I go, I want to show you guys the actual output code so you can kind of see and get an idea of how things look. So I'm going to show you a UType of both a function pointer with an optional argument. And so we're going to have one that's going to have an actual argument, and we're going to have another that doesn't have the actual argument name. And then we're going to also have a type of an array, and then I can also do like a var as just a single type. So you can kind of see how variable declarations are created, and you can look at the UType formatting to see how it is in the actual AST. So if I come down here, put the breakpoint, and run the code, I can actually check to see how things look. And when we scroll up, we kind of see what's going on. So we have our home class declaration. We have our block, which then contains 3 ASTs because we have 3 variables. We have 1 variable declaration, 2, and 3. So the first variable declaration is very simple. It starts out as an object array, so we have our name here for our tokens. Then we have our UType, which is what we're looking for. This is the important part. So we have our brackets. So when we are parsing this on the back end, you want to have this code in here to denote that the UType is of an array type. So that's why we add those characters. Then we parse a type identifier, and it's an object. So that's all it is. Just that token rests in that AST. Now, if we scroll down to var, it's extremely simple. It's even more easier than the last one. We create our second address variable. Now, obviously, the compiler wouldn't like this. It might have to be like address1 or something, so it doesn't like conflict. But that's besides the point. You can see we have our variable here with the same information we had at the top. When we look at the UType, all you can see that we have is a var. We don't have any tokens because it's not an array. So that's how that looks. Now let's scroll down to this. This one's a lot more complicated. So when we put everything together that we learned today, we can see that a variable declaration of pointer of a function pointer has a big UType. It's pretty huge. So we have our type identifier, which represents this whole thing here. Then we have our function pointer, which also represents this. Then we have our UType arg list optional. So that represents this information here. And in there, we have 2 ASTs because we have 2 arguments here. We have this one and this one. So our first UType arg, we have arg, which makes sense. So we have the token, and then in the UType, we have our type identifier. It's not an array. Then we have our reference pointer of type string. So we have that, and then we have our second UType arg, which I think that's everything, yeah. We have our second UType arg, which is a lot simpler. We have our UType here. It doesn't have a name, so if it did have a name, it would be in this tokens list, but it's not, so we don't have that. we have our type identifier, our reference pointer, and then our int. So that makes sense. And then if it was an array, of course, in our type identifier, I think it would actually be up here in the UType. But yeah, you'd have it denoting that it's an array UType. So that's it for today, guys. Hope you enjoyed the video. As per usual, I'm going to go up to the top and go to my handy dandy repository. And if you guys would love to support the channel, definitely watch, star, and fork the repository. This helps out the channel a ton and gives the project a lot more visibility and lets other developers know this project actually exists, which will in turn rank this repository higher up on GitHub. And if you guys would love to stay up to date with the development on the project, definitely check out the remastered branch. Any other branches besides remastered and mastered are pretty stale, so just keep that in mind. This is the branch that I update on almost a daily basis, so definitely check that out. Also, if you'd love to get a little bit more in depth as to what I've done to the language or maybe some stuff that I'm looking to add in the future, definitely check out the docs page or the docs folder and check out the change list file, which will contain all of the things that I've previously added to the language. And you can also check out the roadmap file, which contains everything that I'm planning to add in the future or have already done. So hope you guys enjoyed the video. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. And until next time, I'll see you guys later.